like to just welcome everyone and say thank you for joining us this afternoon. My name is Max Odland. I'm an environmental scientist with the Fire and Resource Assessment Program at CAL FIRE. And I'm very excited to welcome you to this presentation. This series has been going on sporadically for the last few months, and we're going to have more of them coming up this year, presentations from grantees in our Forest Health Research Program. Today, we are joined by Marissa Goodwin, who is going to be presenting about how climate change and drought mortality increase fuel availability and the carbon cost of forest management. Before we get started, I would like to do a brief bit of housekeeping. Again, this meeting is being recorded and the recording will be made available at the website that's listed there. It's our webinars and events webpage. I will also post that in the chat momentarily so that it's easy to find later. A reminder that we'll be doing a Q&A session after the presentation, and for anyone who would like to enter their questions, please enter them in the chat at any point, or go ahead and use the raise your hand function, and I will make sure to call on folks during the Q&A and let you unmute yourself to ask your question in that way. We'll do our best to have all the questions answered. This will be kept to an hour, so if there are further questions, you can always reach out to us and we can put you in touch with the presenter if needed to get more questions answered. With that, I would like to pass it off to my colleague Tadashi, who will say a little bit about the program itself.
Thank you, Max. Can you hear me okay?
Yes.
Great. So yeah, this is one of our, this presentation is coming out of some work that we've funded through our the CAL FIRE Forest Health Research Grant Program. This is a grant program that started, oh gosh, 4 or 5 years ago now. We've had 3+ rounds of grants, and 3 years and an extra sort of round that have funded over 60 projects for approximately $20 million. We're very happy to have been able to support the work at the ongoing work at Tea Kettle, as it is a really important long-term experiment that you'll hear about today. But the mission of the program is, the grant program is to identify and prioritize research topics in forest health and wildland fire science that are critical to the state of California. It's our intent to fund sound scientific studies that support forest landowners and agencies and fire management organizations within the state. And we importantly want to ensure that the scientific information that we generate from those funded projects gets into the hands of decision makers and landowners and those making policy, so that we can have good science supporting good policy. And really all of this is in support of the several guiding documents that we have in the state right now. Importantly, the California Wildfire and Forest Resilience Action Plan, the California Forest Carbon Plan, and the program that supports a good portion of our grants, which is the California Climate Investments Program. I will say that there's probably several people on this call that have been waiting for a while to hear about our next round of grants, so I thank you for your patience. And it is looking like we will be opening a new solicitation here in about 3 weeks. So please keep an eye out, and if you haven't, you're welcome to sign up for the notifications on the FRAP website, the Fire and Resource Assessment Program website, or you can email us at the email address that's at the bottom of the slide there. So thank you. I look forward to hearing from Marissa, and thank you, Max.
Sorry, I was muted there. Thank you, Tadashi. Without further ado, I'll introduce our speaker for today. Marissa Goodwin is the project manager of the Tea Kettle Ecosystem Experiment, a long-term study looking at the effects of mechanical thinning and repeat burning on carbon storage and ecosystem function in a Sierra Nevada mixed conifer forest. She has worked as the project manager at Tea Kettle since 2016, and she is also pursuing a master's degree at the University of New Mexico, where her research focuses on the effects of climate change on forest function and carbon dynamics and how this influences forest management. Thank you very much, Marissa. Please take it away.
Right, I'm going to share my screen here. You all see that?
Yes.
Awesome. All right, well, thank you all for being here today and for taking the time to come to this talk. My name's Marissa. I'm the project manager of the Tea Kettle Experimental Forest in the Southern Sierra Nevada. And today I'm going to be talking about how climate change and tree mortality are increasing fuel availability, and we'll present some of the work we've done at Tea Kettle, looking at how climate change is affecting the carbon dynamics of forest management. So to begin, I'd like to first thank CAL FIRE for funding a lot of the research we've done at Tea Kettle and are continuing to do at Tea Kettle. And I'd also like to acknowledge the Joint Fire Science Program for funding the 15-year post-treatment data collection and research efforts we had at Tea Kettle as well. I'd like to thank my boss and advisor, Matt Hurteau, as well as my other collaborators, Malcolm North and Harold Zald, who contributed to the two studies I'm going to talk about today. And then finally, I'd just like to acknowledge all the field crews who have worked at Tea Kettle over the past 2 decades, because those crew members and all their hard work are what make long-term studies like Tea Kettle possible. So I just wanted to start with that. But yeah, as I'm sure we are all too well aware, we have seen an increase in the size and severity of wildfire in California and across the western US in recent decades. And the fire season has now become characterized by large catastrophic wildfires that are occurring every year. And so this figure here is showing increasing fire size in California over the past 4 decades, with fire size on the y-axis and year on the x-axis. And what you can see is increasing fire size through time, as well as increases in the amount of area burned at high severity. So that's that increase in the portion of the bar that is red. But what I also want to point out here was just how bad the 2020 fire season was. This is the last bar on the right in the bar graph. And I want to highlight this because this is a fire season I'm going to talk about later in my talk. But we know that these increases in fire size and severity are in part driven by a legacy of fire suppression in western forests, which have increased tree densities and surface fuel loads. But increases in fire size and severity are also a result of climate change. And so climate change is contributing to increases in wildfire activity in a couple of different ways. It's getting hotter, and it's staying warmer longer, which lengthens the fire season. And it's also becoming drier, and this is due to rising temperatures as well as changes in precipitation regimes. So in montane forests of California, we're seeing more years with below average winter snowpack. And as temperatures have increased, so has the vapor pressure deficit of the atmosphere. And so the vapor pressure deficit, or VPD as it's denoted on this figure here, is the strength with which the atmosphere is pulling moisture from soils and fuels and live vegetation through evaporation and transpiration. And there is a well-documented relationship between rising vapor pressure deficits and increasing fire size. And that's what you can see here in this figure on the right. And this relationship is largely driven by the fact that as temperatures rise and VPD increases, fuel loads are becoming drier. And as I mentioned on the last slide, climate change is also altering precipitation regimes and increasing the frequency, duration, and severity of drought events across the western US. And as a result, we're witnessing hotter and drier droughts that occur more often and last longer. And we've seen this dynamic play out over the past decade in California, starting with the occurrence of the 2012 to 2016 drought, which was the worst drought period to occur in the state over the past 1,200 years. And the forests in the Sierra Nevada, which is where my work focuses, continue to face significant variability in precipitation as a result of climate change. So looking at this image here on the right, we can see that since the end of the drought in 2016, we've seen what we call hydrological whiplash, where wet years shown in blue are often followed by very dry years shown in white. And in addition to these more frequent and more prolonged drought events, rising temperatures mean it stays warmer longer, and that's led to an increase in bark beetle outbreaks in California forests. And both the drought and bark beetles lead to tree mortality. And so in the southern Sierra Nevada of California, the 2012 to 2016 drought and bark beetle outbreak that occurred around the same time killed an estimated 58% of trees in the Sierra National Forest. And this change in climate and associated tree mortality has important consequences for the carbon dynamics and carbon storage of Sierra Nevada forests. And the carbon dynamics of forests are important because trees take up carbon in the form of CO2 from the atmosphere through photosynthesis, and then they sequester that carbon as biomass in the form of carbohydrates. So you may hear me refer to both biomass and carbon throughout this talk, sometimes interchangeably, and that's because anywhere from 30 to 50% of plant biomass is carbon. So that includes live trees, dead trees, logs, and leaf litter. And we often think of forests in terms of carbon because forests are the largest terrestrial carbon sinks, and they play an important role in offsetting the carbon we emit as greenhouse gases. And carbon is also the currency we use when we think about the costs and gains of forest management. So in forests of the Sierra Nevada, we primarily use prescribed fire and mechanical thinning as management tools to reduce the risk of high severity fire. And both of these management tools have carbon costs associated with them. Prescribed burning emits carbon to the atmosphere, and then thinning physically removes carbon from the landscape. But those carbon costs are offset by preventing high severity wildfire, which would emit far more carbon into the atmosphere than a prescribed burn would, and also prevents the loss of these forests as carbon sinks. And that's what I'm showing you in these two photos on the right. And the amount of carbon that is capable of being stored by a forest ecosystem, or what we call the carbon carrying capacity of a forest, is determined by two factors. So one is the prevailing natural disturbance regime, and the other is the prevailing climate. And so in historically frequent fire forests, like the forests we have in the Sierras, regular wildfire modulated the amplitude of change in the live tree carbon stocks over a fire return interval. So in this diagram, the red dashed line represents the carbon carrying capacity of this forest ecosystem, and then that blue line represents the live tree carbon stock. And through time, there are increases in the live tree carbon stock, coinciding with years of high productivity, often wetter and cooler years. And this was then punctuated by the occurrence of low and mixed severity wildfire, which would decrease the live tree carbon stock by consuming small trees that had grown in during those more productive years. And these wildfires were characterized by low overstory mortality, and the reduction in tree density from wildfire allowed more carbon to be sequestered by the trees that remained on the landscape. And so overall, this regular burning resulted in forest carbon stocks that were stable over both spatial scales and time scales. But humans have altered both drivers of the carbon carrying capacity in frequent fire forests, and we've altered the natural disturbance regime through fire suppression. And so as a result, over the past century, there hasn't been that regular fluctuation in the live tree carbon stock from wildfire. And instead, there's been this steady increase in the amount of carbon that's stored in these ecosystems. And this overshoot of the carbon carrying capacity results in what we call a carbon debt. So this is carbon that is owed to the atmosphere because historically it would have been returned to the atmosphere through regular wildfire. So when you're walking around a frequent fire forest that hasn't experienced fire in over a century, the forest is very dense. And so there's a lot of small and medium diameter trees that have grown in the absence of wildfire. And in the Sierra Nevada, this is that ingrowth of white fir and incense cedar. And all of these trees constitute that carbon debt, and they create a continuous vertical fuel structure, or what we call ladder fuels, and that's what you can see here on the right. And as a result, when wildfire does occur, it burns at high severity and it consumes the overstory. But the other way humans are altering the carbon carrying capacity of forests is through climate change. And as I've already mentioned, the duration and severity of droughts are increasing with climate change, as well as the occurrence of pest and pathogen outbreaks, both of which lead to widespread tree mortality events. And so now in this diagram, we have that increase in the live tree carbon stock that resulted from fire suppression. And after a drought event or a bark beetle outbreak, we see a significant decrease in the live tree carbon stock. And the live trees that are lost through tree mortality are not removed from the landscape, and they instead transition into dead trees and then into surface fuel carbon pools as trees begin to drop their needles or their branches or fall to the ground altogether. And so that carbon debt remains on the landscape, but it's been reallocated into different carbon pools now. And so if you've driven through the Sierra Nevada in recent years or hiked through a forest that's experienced a lot of tree mortality, you know what this transition looks like. So following the 2012 to 2016 drought, there are now a substantial number of standing dead trees in these forests, and we're also seeing increases to the surface fuel loads from drought-related fuel inputs. And we've also seen this dynamic play out in data that's been collected in the Sierra Nevada following the 2012 to 16 drought and bark beetle outbreak. And so this figure here contains FIA plot data showing the change in dead basal area in the Southern Sierras before and after the 2012 to 2016 drought. So FIA plots are measured every 10 years, and the plots shown here are mixed conifer plots that were measured before and after the drought. So that one-to-one trend line on the figure represents no change in dead basal area after the drought. And what we can see here is that most of the plots fall above that one-to-one trend line, indicating an increase in dead basal area following the drought. And this figure on the right now shows carbon data from plots at the Tea Kettle Experimental Forest in the Southern Sierras. And I'm going to talk more about this research site and its experimental design later in the talk. But for now, I just want to mention that we have 6 different treatment types at Tea Kettle, which are what the different panels represent. And so this figure shows the increase in dead biomass across all of our research plots following the 2012 to 2016 drought. So we have year on the x-axis and carbon biomass on the y-axis, and the red arrows are pointing to the year 2017, which was the first year the plots were measured following the drought. And when you compare this to 2011, the measurement period before the drought, we see a substantial transition of live biomass, shown in green, to dead biomass, shown in brown, following the drought period. And this transition of trees to, or this transition of live trees, I should say, to dead trees and surface fuels results in a substantial amount of biomass and carbon transitioning to fuel types that are readily available to burn. And so fuel availability, or the amount of fuel that is available to burn during a fire, is a function of fuel moisture. And this is because fuel moisture governs the amount of time and energy that is required to vaporize the water stored in fuel in order for ignition to occur. And so wetter fuels, for example, a log with a fuel moisture content closer to 50%, requires more time and more energy to ignite those logs, and as a result, less of that log biomass is likely to be consumed. But as fuels become drier, the ease with which they can ignite increases, resulting in more biomass that can be consumed. And we know that climate change is reducing the fuel moisture content of both live and dead fuels, resulting in increasing fuel aridity or fuel dryness. And when you couple this increase in fuel aridity with that transition of live biomass to dead biomass, you get these abundant fuel loads that are readily available to burn. And that's because dead trees and surface fuels have inherently lower fuel moisture contents than live trees. And that's because they're just not actively taking up water from the soil. And so looking at the x-axis for each graph here, in dry mixed conifer forests, dead fuel moisture contents typically range from about 10 to 50%, whereas live conifer trees, I'm showing lodgepole pine data here, ranges from about 110 to 150%. And you can see on the y-axis for each graph that this difference in fuel moisture content results in significant differences in the proportion of these fuels that are likely to be consumed during a fire event. And so for wetter live fuels, you're looking at about a 17% consumption, whereas for wetter dead fuels, that consumption is about 45%. And as I mentioned before, climate change is decreasing the moisture content of both live and dead fuels. But what we can see here in these two figures is that equal reductions in fuel moisture content for live and dead fuels don't result in equal increases to the proportion of fuel that's available to burn. So while a 40% decrease in fuel moisture content results in only a 6 to 7% increase in live fuel availability, it would result in a 38% increase in the fuel availability of dead fuels. And so in these two figures, the change in fuel moisture content is the same on the x-axis, but the change in the range of the proportion of fuel that's available to be consumed, that's depicted on the y-axis, is significantly different between these two fuel types. And this is the same figure now, but with fire radiative energy on the y-axis. So when a fuel is consumed in a fire, it releases heat. And this is an important thing to consider because heat energy is primarily responsible for preheating and dehydrating fuels surrounding a wildfire, and increases in heat energy release can facilitate fuel ignition and wildfire spread. And so in the data presented here, I held biomass constant, but what you can see is that 2 times as much heat energy will be released from dead fuels compared to live fuels. And this is a function of dead fuel having lower fuel moisture content and higher fuel availability. And so what this means is that fires that occur where there's a surplus of standing dead trees or fallen logs may release large quantities of energy as heat, and they may produce wildfires that are characterized by their unprecedented size, intensity, and rates of spread. And so to recap all these concepts before I move forward, tree mortality from drought and bark beetle outbreaks are transitioning large amounts of live fuels to dead fuel pools. And while climate change is decreasing the fuel moisture content of both live and dead fuels are inherently drier than live fuels, and they now are becoming even drier with climate change. And these dead fuels dry out, or as these dead fuels dry out, they become more readily available to burn and will release more energy as heat when wildfire occurs. And because heat energy release plays an important role in wildfire spread, fires that occur where there's a lot of dead and dry fuels can produce megafires that are characterized by high intensity and high rates of spread. And so my collaborators and I uh, decided to work on a project that looked at the 2020 fire season to investigate how the combined effects of tree mortality and climate change may have influenced fuel aridity and heat energy release during two specific wildfire events. So for this project, we looked at two fires from the 2020 fire season. We looked at the Cameron Peak Fire in the Colorado Rocky Mountains and the Creek Fire in the Sierra Nevada of California. And so when they occurred, both of these fires were the largest single fires to have occurred in their respective states, and they were characterized by alarming rates of fire spread. And additionally, both of these fires occurred in areas that had experienced substantial tree mortality. So the Creek Fire occurred in an area where the 2012 to 2016 California drought and subsequent bark beetle outbreak resulted in widespread tree mortality. And then the Cameron Peak Fire in Colorado burned through forests that had experienced large numbers of bark beetle killed tree from mountain pine beetles. And so for this project, to look at climate-driven changes in fuel moisture content and heat energy release, we use daily maximum temperature, 1,000-hour fuel moisture, and energy release component data from GridMet to assess changes in dead fuel moisture content and energy release over the past 3 decades within the footprints of both of these two fires. And so in this figure, the Creek Fire footprint is shown in the top row and the Cameron Peak Fire is shown in the bottom row of the figure. And 1,000-hour fuel moisture content is the moisture content of logs. And that's usually similar to the fuel moisture content of standing dead trees. And then ERC, or the energy release component, is a measure of available energy per unit area, and that contributes to fire intensity and fire spread. And so we looked at 3 time periods for this study: the end of the 20th century, so 1990 to 1999, and that's shown in solid blue. We then looked at a drought period for each forest, so that was 2012 to 2016 for the Sierras and 2001 to 2009 for the Rocky Mountains, and that's shown with the yellow dashed line. And then 2020, which was the year each fire occurred, and that's shown with the dotted black line. And so what we found was that compared to the end of the 20th century, monthly temperature maximums from April to October in the southern Sierras and in the Rockies have increased in recent years. And so this is shown in the first 2 panels. And this increase in temperature during periods of drought and in 2020 corresponded to decreases in 1,000-hour fuel moisture content during these time periods, and that's shown in the middle 2 panels. So notice that the black dotted line representing 2020 is lower than the yellow line depicting the drought periods and the blue line showing the turn of the century. And these decreases in fuel moisture content during periods of drought and in 2020 resulted in higher calculated ERC values for the areas where the Creek Fire and Cameron Peak Fire occurred. So you can see the black line for 2020 in the last 2 panels is much higher than the other 2 lines, indicating high amounts of energy capable of being released both where and when these 2 fires occurred. So for the next part of the study, we just used fuels data and climate data for the Southern Sierras, and we found that decreases in fuel moisture content over the past 2 decades has resulted in higher calculated fire radiative energy values, shown in portion C of this figure, and a greater proportion of biomass that's available to burn, shown in portion D of the figure. And this suggests that temperature-driven reductions in dead fuel moisture content increase both fuel availability and energy release in the region where the Creek Fire burned. And so walking you through this figure, in panel A, we see that temperatures were higher in 2020 than they were during the 2012 to 2016 drought and during the turn of the century. And these high temperatures correspond to lower fuel moisture contents in 2020. So in panel B, you see that black dotted line is lower than the blue and yellow lines. And then these dry fuel loads in 2020 correspond to higher calculated fire radiative energy values and a higher proportion of fuel available to burn. And that's what you see in panels C and D. And in both these panels, the black dotted line representing 2020 is higher than both the yellow line for the drought and the blue line for the turn of the century. But so far, these comparisons have only focused on how climate change is decreasing fuel moisture and increasing energy release, so just focusing on that climate change component. So for the final part of our study, we did some calculations to determine the combined effects of both decreasing fuel moisture content and the transition of live fuel to dead fuel on fuel availability and energy release in the area where the Cameron Peak Fire occurred. And we focused on this fire in particular because that's the area we had the most data for. So we looked at live and dead fuel moisture averages for live lodgepole pine and 1,000-hour fuels in the Rocky Mountains and found that fuel moisture contents have decreased by about 5% over the past 15 years due to climate change. And this reduction in fuel moisture content by 5% results in a 1% increase in live fuel availability, but a 7% increase in dead fuel availability. So climate-driven reductions in fuel moisture content are increasing dead fuel availability more so than live fuel availability. But now let's consider the effect of climate and the effects of live fuel becoming dead fuel on fuel availability and energy release. And so this results in a 108% decrease in fuel moisture content. So a live fuel 15 years ago had a fuel moisture content of about 120%, and that fuel is now becoming a dead fuel with about a 12% fuel moisture content. And this transition and this drastic change in moisture content results in a 55% increase in fuel availability within the footprint of the Cameron Peak Fire and a 100% increase in the amount of heat energy that could be released within that footprint as well. And so in other words, climate change plus tree mortality that's occurred in this region over the past 2 decades resulted in a twofold increase to the amount of heat energy that could be released where and when the Cameron Peak Fire occurred. And so overall, these results, combined with fire transport models that relate heat energy release to fire behavior and spread, suggests that tree mortality and rising temperatures may be significant contributors to the unprecedented wildfire behavior we've witnessed in recent years, and specifically during these 2 fire events. So our results support the trends shown by other studies that rising temperatures over the past few decades have contributed to decreases in fuel moisture content. But our results also show that the combined effects of rising temperatures and tree mortality result in substantial decreases to fuel moisture content in these mortality-ridden forests. And the substantial amount of heat energy that is released from fires that occur where there's a surplus of dry and dead fuels can generate a positive feedback loop for wildfire spread. And this can make these wildfires incredibly difficult to control. So our results suggest that the abundant dead and dry fuel loads that are produced by climate-driven tree mortality and climate-driven fuel aridity may result in wildfires that are perpetuated not only by available fuels, but also by the substantial amounts of energy these fires release as heat. And so while there is this increasing risk of high severity wildfire, given these widespread increases in dead fuel loads across California and across the Sierra Nevada forests, we do know that management practices like prescribed burning and thinning can start to chip away at the substantial amount of both live and dead biomass that's on the landscape. And so prescribed burning can help reduce the risk of high severity fire by consuming surface fuels in small trees. And then mechanical thinning, on the other hand, reduces tree densities in ladder fuels by removing trees from the landscape. And then another important component of management in frequent fire forests is that the reintroduction of fire will utilize repeat burning to approximate the historic fire return interval. So because there's been about a century of fire deficit in these landscapes, repeat burning is necessary to restore forest structure and to restore fire as an ecological process. And the expectation with repeat burning is that carbon emissions will decrease with each additional burn due to the reduction in available fuel from that previous burn. But since tree mortality is transitioning a lot of biomass to dead tree and surface fuel pools, it's unclear if this expectation is going to hold under climate change. And the other thing I want to point out here is that in addition to thinning and burning practices, reducing the amount of fuel that's on the landscape and mitigating the risk of high severity fire, these management practices may also mitigate tree mortality during severe drought events by reducing competition. And so this figure here is from a study led by Derek Young, which found that mortality rates during the 2012 to 2016 drought increased with competition. And so in the figure, FDCI scores are a measure of competition, and high competition is indicated by a high FDCI value, or the areas shown in orange and red. And the greater the value, the greater the competition between trees. And so in portion A of this figure, we can see that the number of dead trees increases with increases in the FDCI value. And other studies have also found that trees growing in less competitive growing environments are more resilient to drought and exhibit higher growth rates and lower mortality rates during drought events. But as droughts become hotter and more prolonged with climate change, it's unclear if these management practices are going to be enough to limit mortality during these extreme drought events. So for the next study I'm going to highlight, we use the long-term experiment that's being conducted at the Tea Kettle Experimental Forest to look at forest carbon dynamics during the 2012 to 2016 California drought to assess how different forest management techniques may increase drought resistance and also increase carbon stability. And in this study, we also looked at the carbon emissions of a second entry prescribed burn that followed the drought to investigate how climate change may be altering the carbon cost of different management techniques. And so the Tea Kettle Forest is an old-growth forest in the southern Sierra Nevada. It's located within the Sierra National Forest, about 80 kilometers east of Fresno, California. So for reference, it falls between Yosemite and Kings Canyon National Parks. And the tea kettle experiment was established back in 1997 to look at the effects of thinning and burning on ecosystem function in a mixed conifer forest. And we know from initial surveys of fire scars at Tea Kettle that the historic fire return interval at this site used to be every 12 to 17 years, but the last wildfire to occur in this area was in 1865. And so the experimental design at Tea Kettle includes 6 treatment types consisting of 2 levels of burning, so we have burned and unburned plots, crossed with 3 levels of thinning. So we have an overstory thin, an understory thin, and then no thin. And you'll see this combination written out as burn slash the thinning treatment or just the thinning treatment in the results I present moving forward. But the overstory thin removed all trees greater than 25 centimeters in diameter, leaving behind about 22 of the largest trees per hectare. And then the understory thin removed all trees between 25 and 75 centimeters in diameter. And this is a thinning treatment that was designed for the California spotted owl because by just removing the midstory of trees, it retains adequate canopy cover and habitat for this species. So each treatment was replicated over 3 plots, each 4 hectares in size. So we have a total of 18 treatment units, and the distribution of the treatments and their replicates is shown here in the map on the right. And so our thinning treatments occurred in 2000 and the summer of 2001, and then the first entry prescribed fire was implemented in the fall of 2001. And then a second entry burn was implemented in the fall of 2017. So that occurred 16 years after that first burn to approximate the fire return interval for the site. And these 6 treatments varied in intensity of how much live tree biomass was removed, especially with respect to those different thinning treatments. So that resulted in different amounts of live tree carbon across the different treatments post-treatment. And so you can see that here in this conceptual figure showing different decreases in the live tree carbon stock following treatment. And so to measure the amount of carbon stored in each treatment type and to follow tree survival through time, we mapped and measured each treatment unit and then measured trees pre-treatment, post-treatment, 10 years post-treatment, 15 years post-treatment, and then in the 2 years following the second entry prescribed burn. And the resulting STEM maps allowed us to follow tree mortality through time, as well as calculate growing space for individual trees. And additionally, surface fuel loads were measured during all of those measurement periods at 9 preset grid points in each treatment replicate. So surface fuel loads were measured using Brown's transect surveys, where you take measurements of the leaf litter depth, and then you count the number of sticks and logs that intersect the transect. And for logs that are greater than 7 centimeters in diameter, you obtain more data for them. So you measure their diameter, you record their species, and also their status of decay. And so needles and leaves are referred to as litter. Sticks smaller than the size of your wrist are what we call fine woody debris. And then logs greater than the size of your wrist are called coarse woody debris. And that ranges from something the size of your wrist up to a log that's almost as tall as you are, as you can see in this middle photo at the bottom of the slide. And so we then plug these STEM measurements and fuel quantities into allometric equations to calculate the amount of carbon stored in live and dead fuels, as well as surface fuel loads. And the carbon currency we use is megagrams of carbon per hectare. And so the goals of this study were twofold. The first goal was to quantify the effects of the 2012 to 2016 drought on tree survival. And so we sought to answer the question, does tree survival increase with increasing treatment intensity? And the second goal of our study was to quantify the carbon dynamics of a second entry prescribed burn that occurred after the drought. And so our first hypothesis was that the second entry burn emissions would be lower than the emissions of the first prescribed burn due to a reduction in fuel loads from that initial prescribed burn treatment. And so this was the original hypothesis for the tea kettle experiment before we knew the effects of the 2012 to 2016 drought. And then our second hypothesis for this part of the study was that surface fuel loads would increase after the drought, but the second entry burn would then reduce those surface fuel loads back to pre-drought levels. And so to dive into our results with respect to individual tree survival during the drought period, we found that growing space was a significant predictor of tree survival, with the likelihood of survival increasing with increasing growing space. So in this figure, we have growing space on the x-axis and the probability of survival on the y-axis, with 1 being the tree survived. And to start, I'm just going to focus your attention on the control and burn only treatment. And so for these treatments, you can see increases in the probability of survival for all tree sizes with increasing growing space. However, in the control plots, notice that there is much less variability around the yellow line for large trees greater than 75 centimeters in diameter, or DBH, and that stands for diameter at breast height. And this is because in the control plots, there are not many trees with growing areas of 100 meters squared or more. And then conversely, when we look at the burn-only treatment, we see much more variation for large trees, indicated by the confidence interval shading around the yellow line. And that's because burning resulted in more trees having larger growing areas. So I just want you to keep that in mind when I show you the rest of the figure. So now when we consider all treatments, we see that the strength of the probability relationship varied by treatment and tree size. So we found that treatments that involve thinning, such as the understory thin and overstory thin and burn understory thin, had the greatest increases in survival probability for large trees with increasing growing space. So that's shown with that yellow line. But this relationship didn't hold in the burn overstory thin treatment, and it's kind of hard to see in this panel, but we actually saw a decrease in large tree survival probability with increasing growing space. And additionally, we also saw decreases in the survival probability of medium-sized trees in the burn understory and burn overstory thin treatments. We also found that the drought resulted in a reallocation of the carbon stocks across all 6 treatment types. So in this figure, carbon in megagrams per hectare is on the y-axis, and the black dashed line in each panel represents the occurrence of the drought, with 2017 being the first measure year after the drought. And I showed you this figure earlier, but again, what we see here is that across all treatments, there's a decrease in live tree carbon, shown in green in 2017, and corresponding increases in dead tree and surface fuel carbon, shown in brown and tan. And we found significant differences in the magnitude of live tree carbon decreases and dead tree carbon increases between treatments. And that's likely a result of the different effects of each treatment on tree survival, which I showed you in the last slide. But for example, the loss of live tree carbon is greater in the control and burn only treatment compared to the overstory thin and understory thin treatments. And this increase in dead tree and surface fuel carbon pools from drought mortality resulted in higher second entry burn emissions in 2 of our 3 burn treatments when compared to emissions from that first entry burn. So we calculated burn emissions by subtracting post-burn total carbon from pre-burn total carbon. And each panel here represents each burn treatment. And then on the x-axis, we have the first entry burn compared to the second entry burn. And what you can see was that the second entry burn emissions were higher than the first entry burn for both the burn only and burn understory thin treatments. And the second entry burn was also characterized by higher consumption of dead trees and surface fuel carbon when compared to that first entry burn. And so this suggests that the drought's effects on carbon distribution influence the carbon dynamics and carbon emissions of our second entry prescribed burn. And before I move on to the next slide, I also want to point out that the burn understory thin treatment saw the greatest increases in second entry burn emissions. And one explanation for the burn understory thin treatment having the highest second entry burn emissions was the high amount of drought-related snagfall experienced by this treatment. So this figure is showing the probability that trees that died during the drought became surface fuel during that same period by treatment and tree size. And so a value closer to 1 on the y-axis indicates a greater probability of a snag becoming a surface fuel, snag being a standing dead tree. And again, dBH means diameter at rest height. And the burn understory thin treatment, shown by that upper blue line, had the highest probability of snagfall for large trees compared to other treatments. And this treatment also had the greatest proportion of dead tree carbon becoming coarse woody debris carbon, with 15% of the carbon in trees that died during the drought becoming surface fuel carbon by 2017. So with respect to our second hypothesis for the second entry burn, we did find that the burn successfully reduced surface fuel loads back to pre-drought levels. So on the y-axis here, we have carbon in megagrams per hectare, and each bar consists of the different surface fuel types. So 1, 10, and 100-hour fuels are fine woody debris, and then 1,000-hour fuels are coarse woody debris or logs. And the black dash line represents the occurrence of the drought, and 2017 is the measure year that occurred after the drought and before the second entry burn. And so after the drought, we see significant increases in 1,000-hour fuel loads across all treatment types, and that's shown by the increase in dark blue in those bars. But then after the second entry burn, these fuel loads have been reduced back to pre-drought levels in the burn plots as shown in these lower 3 panels. But in the unburned plots, which are the upper 3 panels, the surface fuel loads remain high, and that elevates the risk of wildfire. So going back to the concept I presented earlier, these surface fuel loads represent biomass that is dry and readily available for consumption if wildfire were to occur. But to tie this all together, I'd like to return back to the concept of the carbon carrying capacity, or the amount of live carbon capable of being stored by a forest. So unlike the figure I showed you earlier, which showed the absolute carbon values for each treatment, this figure is showing the live tree, dead tree, and surface fuel carbon stocks as a proportion of the total carbon for each treatment. And what you can see is an almost identical trend across all treatments, with live tree carbon decreasing and dead tree and surface fuel carbon increasing after the drought. And what this finding suggests is that we can expect reductions in the carbon carrying capacity of both managed and unmanaged forests as they equilibrate to extreme climatic events like drought events. And so overall, the results of both of these studies suggest that the carbon carrying capacity of Sierra Nevada forests and Western forests in general will decrease as they equilibrate to climate change. But what this second study indicates is that we will see decreases in the amount of live tree carbon stored in both already managed and unmanaged forests as a result of tree mortality, suggesting that these treatments are not going to be enough to completely buffer forests from the effects of climate change. And again, as the carbon carrying capacity decreases, we can expect to see substantial amounts of live biomass transitioning to dead tree and surface fuel pools. The results of this last study do indicate that prescribed fire can reduce the risk of wildfire associated with drought-related fuel inputs by consuming dead trees and surface fuels. But the expectation that carbon emissions will decrease with subsequent management may no longer hold with ongoing climate change, and we should expect to see increases in the cost of both initial and repeat management in Sierra Nevada forests. And so given that a lot of the policies that govern the carbon costs and gains of forest management often penalize carbon emissions from prescribed fire, our results suggest that we need to rethink these policies and the carbon costs of forest management with ongoing climate change. And so I'd like to finish off by talking about some future CAL FIRE funded research that's going to be conducted at the Tea Kettle Experimental Forest on this topic. So we're gearing up to implement a catchment-wide prescribed burn in the untreated portion of the Tea Kettle Forest. So we'll be burning about 200 hectares of the Tea Kettle Creek watershed, which hasn't burned since 1865, and it's experienced significant amounts of drought mortality. And so for this project, we're going to be looking at the effects of drought mortality and topography on fire behavior, consumption patterns, and carbon emissions. But I'm going to end with the results of our pretreatment data collection for this project. So in the summers of 2021 and 2022, we conducted STEM surveys and fuel surveys across 200 plots in the new study area and used this data to calculate the amount of carbon stored in different fuel pools. And what you can see in this figure is that there is more dead biomass in this forest than live biomass, the gray and tan colors compared to the green portion of the figure, which represents live tree carbon. And on top of that, our data captured a substantial increase in coarse woody debris from snagfall in just a year's time. So in 2020, we were able to identify logs in our fuels transects that had fallen since the year prior. And from 2021 to 2022, coarse woody debris carbon increased by 6.5 megagrams of carbon per hectare, which was an almost 20% increase in surface fuel loads from the year prior. And so I leave you with this because I think it captures the challenges we face with forest management and specifically prescribed fire moving forward. Dead fuels are becoming drier and more abundant with climate change, and that increases the risk of fires burning hot and spreading quickly. And that risk applies to both wildfire and prescribed fire. And dealing with these abundant dead fuel loads may require adjustments to our management approaches to prevent crown's torching and substantial overstory mortality when we burn in these areas with significant amounts of dead fuels. And so these areas may require regular burning at smaller scales to start to chip away at dead fuel loads. But also because of the amount of fuel that's in these forests and the rate at which dead trees are becoming surface fuels, we may also need to rethink the fire return interval when it comes to repeat burning to chip away at these fuel inputs in a timely manner. But finally, when it comes to the carbon costs of forest management or the emissions associated with prescribed burning, we need to recognize that the carbon cost of prescribed burning is likely to be a lot higher than it was 10 to 20 years ago as a result of drought and bark beetle mortalities. And our policies surrounding the use of prescribed fire need to account for that. Um, Thank you all for listening. Hopefully there's time to get to some questions, but if you'd like to email me, my contact information is below. And there's also a QR code here if you'd like to check out the papers I talked about today. And there's also a bunch of other papers that have been from the Tea Kettle Experimental Forest over the last 5 years on my Google Scholar page as well. So feel free to check those out. Thank you everyone for listening.
Thank you very much, Marissa. It's been wonderful to hear about the research there. It looks like you are still, okay, perfect. I was just gonna mention your screen was still shared there. At this point, we are going to switch over to question and answer. So we are going to stop recording, and we do have a few minutes for questions here. A reminder, we do already have